Stanford University.
Okay, we have 10 minutes for schmoozing. Yes.
You made a comment last time that horizons are always hot.
Okay, well, yes, I did.
So, in a scenario where you've just got a,
What in the,
in a horizon of, I guess what do you call it, the consider, or a universe horizon, how is it hot? I mean, like, how would
do you mean how hot is it or how is it hot?
how is it hot? Like, what's the mechanism of it being hot?
Okay. Exactly the same as in the black hole. Does that help you? All right, let's.
The black hole, I kind of see the energy of gravity and all this stuff, right? You say, okay, there's some heat.
All right. You know, that's pretty much exactly what I was going to start the lecture with tonight. So make sure I start on that. But I'm going to defer it until 7 because that was about where I was going to begin.
On the black hole,
Yeah.
on the black hole temperature, you said you lowered the thermometer
Right.
near the horizon, it gets hotter.
Yeah.
If you did that experiment where you shot photons at the black hole to build it up,
Yes.
and you would still measure the same entropy?
Entropy, let's be precise. There's entropy, there's energy, there's temperature. What are you asking exactly?
First, you would measure the same entropy because it would still be the same probability of the photon either being captured or missing.
After the photon falls into the horizon or onto the horizon or whatever you want to call it, the entropy or the hidden information, if you like, the information that's inaccessible to you because it's either inside the black hole or from your perspective very, very close to the horizon and it would take forever for a photon to get out, the information that's hidden is one more bit. So every time you drop a single photon in, the entropy increases by 1 unit.
So it's the energy that you're arguing, is it like you're seeing a higher frequency photon because you're near the horizon?
Yes, yes, yes. The question about the temperature of horizons, well, let me answer it now. The horizon is always hot. We're going to come back to it in a minute. The horizon is always hot in the sense that if you lower the thermometer down, you would always detect a very, very high temperature as you get very close to the horizon. So you can think of it as the horizon being a place or surface of extremely high temperature, which is constantly emitting and reabsorbing photons. They're really quantum fluctuations, and they're really nothing more than the high-frequency quantum fluctuations that are taking place in a small volume of space, in a small region of space. The horizon makes them real in a way which I'll come to, which we're going to talk about, makes them real thermal fluctuations in a rather interesting way. But every horizon always has the property that the temperature, the actual temperature of a real thermometer lowered down to the horizon would record a temperature which would be 1 divided by 2 pi times the distance to the horizon in the denominator. Every horizon, whether it's a black hole horizon or any other kind, always has that property. You asked me a question now. I can't remember exactly what it was.
I think when you're near the horizon,
Yeah.
the time sort of freezes. Does that mean that the photon that came in to build up?
Yeah. Let's forget the photon that came in to build it up. Let's talk about the photons which are being emitted. Why, when you stand far from the horizon, does the horizon not, or does the radiation that hits you, why isn't it this very high frequency radiation that is emitted very close to the horizon? In other words, you drop a thermometer down, you discover that the region near the horizon, the so-called near horizon region, is very, very hot. Why isn't it hot far away? I can assure you, if we created a blank wall over there, or that wall, and we heated it up to some very, very high temperature, and let's suppose it was a very, very big wall, and we heated it up to some high temperature, I don't think it would make much sense to say that as we moved away from the wall, that the temperature went down like 1 over the distance. It wouldn't. You would be blinded by high-frequency photons pretty much no matter how far you got from that wall. The high-frequency photons that came out of it, the gamma rays, the super gamma rays, everything else that came out of it, would blind you pretty much no matter how far you got from this very, very large wall. Why is it that that doesn't happen with the horizon of a black hole? Why, when you stand back from it and get a good deal of distance between you and the horizon, why don't you get blinded by these very high frequency photons? And the answer? What's the answer? Redshift. Redshift. The redshift is another way of saying that as the photons propagate away from the horizon, they lose energy. And they lose energy for exactly the same reason, kinetic energy. They lose energy for exactly the same reason that this piece of chalk does when you throw it up in the air. It is doing work, or you have to, in order to raise it, you have to do work against the gravitational field. And if you don't do work to keep it moving with the same velocity, then the velocity will slow down. Well, with photons, don't think about velocity. Velocity is the wrong thing to think about. Think about energy. For a non-relativistic piece of chalk, there's a close relationship between its velocity and its energy. But what's really happening is it's losing energy. Right? For a photon, the relation between velocity and energy is different. Namely, the velocity is always the speed of light, and the energy is the energy. But it's still true that as the photon climbs out of the gravitational influence of the black hole, it loses energy. So in the transit between the horizon, very near the horizon where it's very hot, and far away, the photon loses an amount of energy such that a distant observer doesn't see the black hole as being very hot. He sees it having the Hawking temperature. And the Hawking temperature decreases with the mass of the black hole. Remember what it was, Hawking temperature of a black hole. And you can think of it as the temperature as seen by somebody looking at the photons or being exposed to the photons very far from the black hole. The temperature, T Hawking, is equal, I'll write the precise formula for no particular reason, but 1 over 8 pi times the mass of the black hole. There is an h bar here, a Planck's constant, and some numbers of factors of c, which I can never remember. C cubed, I can't remember if it's upstairs or downstairs, but
Or just plain H, because the pi's already in the...
I don't remember. I think it's h bar. I think it's h bar. I think it's actually h bar. Right. 8 pi times the mass of the black hole. So the bigger the black hole, the cooler it is. Why does it look cooler for a big black hole? Well, that photon that was created very near the horizon has a more difficult time getting away from the big black hole than a smaller black hole. In other words, it has to do more work, it loses more energy in escaping from a big black hole from the near horizon region than it does for a small black hole. So the effect is the temperature, the effective temperature seen by an observer far away decreases with the mass of the black hole. But if you take this formula, you interpret it in terms of the energy of typical photons. In fact, the temperature of black body radiation, the temperature of thermal radiation, is approximately the same as the typical energy of any given photon. So this just says the photons typically have energy 1 over the mass of the black hole. And if you then trace that inward toward the horizon and say how much energy did the photon have to have when it started out in order to escape and have this much energy when it got out, you'll find the energy is always the same. It's always about this 1/2 pi times the distance from the horizon. How close can you get to the horizon in a meaningful sense? Well, the Planck distance. The Planck distance sets the scale for all quantum mechanical distances. And so you might say then that these photons originated in a thin layer. This is the way it behaves. This is the way the system behaves. In a thin layer, perhaps a Planck length thick, near the horizon or right at the horizon, and it is continuously emitting photons and absorbing photons, emitting and absorbing them. The energy of the photons, as high as you can imagine, the Planck energy. Now, most of those photons don't get out. Most of those photons don't get out. What happens to them? They fall back. All right? Here's the horizon of a large black hole. And if the horizon is hot, it's continuously emitting photons. But though some of those photons go radially out, but very, very few of them, most of them go off at some angle. The ones that go off at an angle are pretty much guaranteed to fall back into the horizon of the black hole. It's only a tiny cone of angles here that the photons will escape. So, in fact, the emission of photons is a very slow process. It's a slow process because most of them don't come out at an angle which is appropriate for them to escape, and most of them simply just fall back to the horizon, fall back because of gravitation. The ones that are coming out can bang into the ones falling in, and guess what happens? They collide, they're very energetic, they make electron-positron pairs, they make everything that you can think about, and they make this thin layer of very, very hot material. It's like no material that we ordinarily encounter in nature, much, much hotter. And the surface of it is continuously emitting photons, which we see as having much, much lower energy than their emission. That's the mathematical theory, that's the consequence of the mathematical theory of horizons. There's another way to think about it. Remember, we've drawn pictures of black holes. The outside of the black hole was out here. The inside of the black hole was in here. Somebody, a given distance from the black hole, is moving along a trajectory which looks like this. Now, there are quantum fluctuations that take place. Without trying to get into the depths of quantum field theory, let's just use the rough metaphor of quantum fluctuations being closed loops of virtual particles. So virtual particles are constantly being created and annihilated. And an observer far away just sees those particles created, doesn't see them actually, it all happens too fast. Right? Here are the lines of constant time. Way out here is t equals infinity. All right, somebody out here, a little fluctuation like that lasts a tiny amount of time. They can be detected. They can be detected by, very high precision quantum electrodynamics and the properties of atoms and so forth. But there are also fluctuations that take place over here. Now, those fluctuations appear to be emitted from the horizon. The horizon is a place very close to this light cone here. They appear to be emitted and fall back into the horizon. That is exactly what these things are. They are the quantum fluctuations which take place half behind the horizon and half in front of the horizon, and look to somebody on the outside as something emitted from the horizon and reabsorbed. Some tiny fraction of them have enough energy to get out, and we call that Hawking radiation.
If you're on the outside, wouldn't you see it go from t minus infinity to t plus infinity?
Sorry again?
When it crosses those 45-degree lines, you said there are t equals the lower ones.
Yeah, well, okay, so let's not, yeah. There's a classical horizon, which really looks like this. But it's always convenient, and we all do this all the time. We draw a surface 1 Planck length away from that horizon. This is a surface 1 Planck length away from the horizon. All right, it's 1 Planck length from here, 1 Planck length here, 1 Planck length here. It's a surface, if you like, if we wanted to draw this a different way, we would say here's the horizon, and 1 Planck length away, a thin layer. And the point here, of course, is that the horizon is not really accurately defined to within a Planck length. Quantum fluctuations not only of ordinary particles, but of gravitation and the structure of the horizon, they all take place. So you really should think of the horizon as a sort of slightly thickened thing. If you think of it thickened like that, and a fluctuation takes place, then this fluctuation doesn't occur at time minus infinity. It occurs at some time in the remote past or in some time in the past. It's emitted out and it falls back into the horizon over here. So somebody outside would say, look, I see some photons that look as though they were emitted from somewhere very close to the horizon with very, very high energy. They pop out and they fall back in. That's what the mathematics gives. And it is the same no matter what the horizon is, whether the horizon is a cosmic horizon, whether it's a... Now, for cosmic... I guess we're ready to begin? Yeah. We have been. 10 after. Oh, we spent more time on that than I thought we would. All right, well then, good. Let's talk about cosmic horizons in the same vein. There are many ways to draw de Sitter space. De Sitter space is the space which is exponentially expanding. One way to draw it is just to draw a time axis which goes up to infinity, draw the blackboard, and keep track of the fact in our heads that the distance between any pair of neighboring coordinate lines here is exponentially increasing with time. That's one way to draw it. Another way to draw it is to squash all of future time down by a coordinate transformation. We did the coordinate transformation last time, so that future infinity is a horizontal line like that. Corresponds to t equals infinity. I think I wrote down the metric for you in a form which maps t equals infinity to a finite place. I'll just rewrite it for you. The original metric was ds squared is equal to minus dt squared, that's the usual thing, plus e to the 2ht dx squared, where again dx squared stands for dx squared plus dy squared plus dz squared. And this e to the 2ht, that's the exponential expansion of the space. Why does it come in with a 2? Because it's really distance squared, right. Distance between points is increasing like e to the ht. And so a given dx corresponds to a growing distance which grows as e to the ht, and in the metric it's e to the 2ht. Then we made a transformation. We made a transformation of the time variable. We wrote the time variable t, I think, what is h? Right. H is the Hubble constant in this space. All right, it's also the expansion rate. We wrote t is equal, I believe, to 1 over h e minus e to the minus a plus, minus h t. Sorry, t, capital T. Capital T goes from minus infinity, is this right? Minus ht? Should be right. Yeah. Capital T goes from minus infinity, deep in the past. What happens to this thing when t goes to minus infinity? It gets big. E to the minus ht gets big when t goes to minus infinity, but it gets big and negative. Okay, so the remote past, t equals minus infinity, is also capital T equals minus infinity. But the remote future, when this t gets very big, that happens when what? Do I have this right? I don't have this right. Excuse me. Still true. When this t is large and negative, this t is also large and negative. All right? But now what happens when this t is large and positive? When this t is large and positive, then this gets small, and capital T goes to 0. So t equals infinity is also capital T equals 0, and this is just a trick. It's a trick for getting the whole geometry, or not the whole geometry, but the part we're interested in, the remote future in this case, onto the blackboard. Now, what happens if we rewrite this metric in terms of t? Let me just remind you, it becomes plus minus dt squared plus dx squared all times 1 over t squared, 1 over t squared h squared to be exact. Notice that when t gets very small, the distance between points gets very big, just as it did on this side over here. This is just a rewriting of this, and t goes to 0 is the remote future. The nice thing about writing the metric this way is that in these coordinates, light rays move on 45-degree angles. That's very helpful in thinking about this geometry and asking who can communicate with whom. Let's get rid of this here. Why is it that light rays move on 45 degrees in this metric here? Well, the rule for light rays is that the metric should be 0, that the interval should be 0. So dt squared minus dt squared plus dx squared equals 0. It's the same as dt equals dx, right? And dt equals dx is just a 45-degree line. If the light ray was moving in the plane, it would be 45 degrees in the plane. If we're moving out of the plane, it would be 45 degrees out of the plane. But there's only so much we can visualize with a two-dimensional blackboard. Okay, so that's the setup. That's what space-time in this kind of inflating, exponentially increasing world looks like. Here it is. Now, let's imagine here's somebody, you, me, I don't know, and in the real world, of course, people only get to live for a certain amount of time, but right now we're going to pretend we can live forever. And so here's the world line of some observer. And that world line, does it really end? No, it doesn't really end because there's an infinite amount of time between any finite point and here. But on the blackboard, we draw the observer as just ending at that point over here. That's the remote future. What can that observer see? Well, he looks back and he sees light rays coming at him from distant places. And light rays move on 45 degrees. I can add one more dimension to this if I can fake a dimension by doing that. All right, so he sees light rays coming, but I can't draw another dimension. That's too many. We would like x, y, and z, but at least I can get x and y on the plane, on the diagram here. So this observer looks back, and as time goes on, gets to see more and more, but never gets to see more of the space-time than is in the backward light cone here. So in particular, never gets to see anything out here or out here. At least doesn't get to see it in any sort of usual sense. So there's a region, most of space and time, almost everything, is totally inaccessible to this observer. Now, of course, there may be another observer over here. And that other observer sees something else. There's some overlap. Okay, there's some overlap. But this person gets to see everything in here. This person gets to see everything over here. Let's simplify it and just study one observer at a time. For all practical purposes, his universe, space-time universe, is this backward light cone here. Now, what does he see? Does he see things, a world which seems to depend on time? You would think so. You might think, well, everything seems to be exponentially expanding. But let's just do a very simple exercise now. Let's consider this distance and compare it with this distance, and this distance, and this distance, and this distance. Basically, this distance that I've drawn here is the distance from the observer to his horizon. Let's see how that changes with time. It looks like it's shrinking, but let's just check that. Here's the metric. Here's the metric, and let's put this point over here at t equals -1. Let's put this point over here at t equals -1/2. This one over here at t equals -1/4. Incidentally, that corresponds to uniform ticking off of proper time. Each unit of proper time would correspond to dividing this interval by half. That's the way this transformation worked. That's why there's an infinite amount of time in here. And now let's calculate this distance. To calculate this distance, we just look at the metric. This is the metric. And so these 2 points are separated by a spatial distance but no time distance. So these 2 points are separated by 0 time interval. That means in this formula here, there should be an equal sign. Somewhere there should be an equal sign. Yeah. There is no time separation at all between these 2 points. So let's write it in a finite form, not a differential form. The square of the distance, let's call it from A to B. What is that? No time separation. What is the delta x between these 2 points? Can you tell? This is a 45-degree angle. This distance is capital T. This distance is also capital T. In fact, let's not even bother writing this t equals -1. Let it just be t. Let it just be t. This distance here, the horizontal distance, is also the same as the vertical distance. So we get 0 from here, but from here we get plus, and delta x is the same as t squared, but now divided by t squared h squared. And what's the answer? 1 over h squared. In other words, the distance from here to here is just 1 over h. That's the actual, real, physical distance that you would measure with measuring devices. But notice the answer doesn't depend on t. The distance between here and here is exactly the same as the distance between here and here. The delta x is smaller, but the t is also smaller. So when you ride up to here, the delta x gets shrunk by a factor of 2, but t also gets shrunk by a factor of 2. So the distance of the observer from the horizon is always the same. The observer sees a horizon around him, a sort of sphere, And that sphere doesn't change with time. In fact, you might suspect that if you used coordinates that were appropriate to the observer inside one horizon, you might discover that the metric had no time dependence. After all, the distance to the horizon doesn't have any time dependence. It's always the same. And in fact, many things don't change with time. It just looks like they do. All right, you might expect that maybe there's some way to rewrite this geometry. And I'm simply going to tell you the answer. I'm not going to work it out. I'm not going to work it out in detail. But using coordinates like this, spatial coordinates which are appropriate to the absolute interior of this horizon region. All right, there is another way of writing the metric, but it's only good for this region. It doesn't capture what's going on the outside, but captures everything on the inside. I'm going to show you what it is. And you look at it for a minute, and it may look somewhat familiar. Familiar but not familiar. These are coordinates which are sort of built on the pattern that I've described here. In other words, they're coordinates in which the coordinate distance between here and here is the same as the coordinate distance between here and here. This coordinate distance and the new coordinates will be the same as this, will be the same as this. And I'll show you what the metric looks like. ds squared equals minus dt squared. That's no surprise. It's actually proper time, actual proper time. And then the rest of it is plus. Oh, no, sorry. I did it wrong. Mistake. I apologize for mistakes, but the mistakes happen when I haven't had my cookies yet. Okay. Minus. What's it?
Understandable.
Yeah, right. Low blood sugar. 1 minus h squared r squared dt squared plus 1 over 1 minus h squared r squared dr squared plus r squared d omega 2 squared. Remember what omega 2 is? Right. When you're sitting at the center and you look around you, you see an angular sphere around you, and this is just one way of not writing out the full spherical metric, just simplifying it. Does this look at all familiar? Yeah, what's it look like? It does. Let me just remind you what Schwarzschild looks like. Exactly the same, except h there, or h squared, is replaced by twice mg, and then it's divided by r. Everything is exactly the same. If you take the parentheses and put this in here, likewise over here. It has the same kind of form. And in fact, it looks awfully different to have h squared r squared here. But the important thing, what was important? Where is the horizon? And the Schwarzschild black, no, right. But the horizon is where this thing is equal to 0. That's the place where clocks slow down. It's the places where distances are infinitely contracted. And it's also the place which separates the inside of the black hole from the outside of the black hole. You can also write this in the form r minus 2mg over r. Doesn't matter how you write it. The real importance of this term is the place where it vanishes, where it equals 0. That is where the horizon is. Likewise here, same idea. The place where this thing vanishes, which is r, where is that? That's r equals 1 over h where is it? R equals 1 over h. That's the distance to the horizon. So this is another way of writing exactly the same geometry, except something really breaks down if you try to make r bigger than 1 over h. Something goes berserk here. You really don't get out past here. The whole metric gets a little bit silly. Space turns into time, turns into space. We don't need to worry about that right now. You let r go from 0 to 1 over h, and this geometry covers the entire cone there, everything that's inside that cone, and it is everything that can be seen by an observer, by a single observer. Yeah?
Why isn't h a function of time?
Well, because you weren't here to begin with. Because we're talking about an exponentially expanding universe. Right. E to the, where the scale factor is e to the ht. Right.
So your series of lines up there, they're all length 1 over h.
These?
Yeah.
No.
Up there next to the drawing above.
Oh, here, the horizontal ones,
Yeah.
yes. They're all length 1 over h, and therefore they're like the distance to the horizon here, from r equals 0 to 1 over h. All right, it takes a little bit of mathematical trickery to rewrite this metric. A few coordinate changes. There's a few transformations of coordinates that you'll have to do. And when you've done those coordinate transformations, you'll find that this patch, it's called sometimes the causal patch or the static patch. And one thing you notice about this metric, the most interesting thing about, or the many interesting things about it, first of all, it has a horizon. But second of all, none of the coefficients here depend on time. They do depend on r, but they don't depend on time. And in that sense, in this form, the metric is completely time independent, and it's another way of saying that what an observer sees around him just doesn't change with time. It's static. It always looks the same. Distance to the horizon is always the same. Whatever the observer does at one time, if he does the same thing at a later time, he'll see the same thing. Now, it is true that if he takes two particles, let's ignore any forces between them. Let's suppose he takes two particles and lets them go. What will happen? No, we're ignoring any attractive forces. Space between them expands, and so they go flying off. So you say, well, that doesn't sound time independent. But the point is, if he does the same experiment at a later time, he will see exactly the same thing. Take the two particles, let them go, and they will slowly accelerate apart from each other. Take two particles at a later time, do exactly the same experiment, they will slowly accelerate away from each other.
Do those two particles see a redshift, the other particle redshift?
Yeah.
Is that right?
For sure. For sure. Now, once we get to this point here, we can kind of see that a black hole horizon and a de Sitter space horizon are very, very close relatives. The fact that everything that you can say about the near horizon region of the Schwarzschild black hole is pretty much the same for the de Sitter space. I'm not going to try to prove that, but the similarity of the metrics are pretty clear, and they, in fact, near the horizon, they're almost identical, very close to the horizon. But the whole global picture of things is quite different. Whereas a black hole is something that we stand on the outside of and look at and emits Hawking radiation, the whole picture here is quite the opposite. We are on the inside. The black stuff is on the outside, the stuff we can't see. And yes, there is Hawking radiation being emitted from the horizon for the same reason. It's emitted and absorbed, emitted and absorbed. Sometimes a photon gets to us. But we can also ask the question, what is the energy of a photon by the time it gets from near the horizon to us? And there is a big redshift factor. This metric, just like the Schwarzschild metric, has associated with it a gravitational potential. This metric also has a gravitational potential. I'll draw it for you. As a function of r. As a function of r, there's a gravitational potential. Let's see if we can draw it. It's upside down. It looks like this. The meaning of that is it takes work to pull something from the horizon to the center. Equivalently, an object emitted from the center as it makes its way toward the center will lose energy, will lose potential energy. It has to climb up out of this potential and will lose energy. Another way of talking about redshift. You can work out the redshift easily enough from the metric. I'm not going to do it now. But a photon emitted near the horizon will lose energy on the way out here, such that the Hawking temperature, the temperature seen over here, is of order, let's see, what is it? Well, it's of order 1 over the distance from the horizon. Of order 1 over the distance from the horizon in Planck units. All right, how big is our horizon? How big is the horizon, our horizon? Our horizon, meaning to say the horizon that we think we know about on the basis of the known expansion properties of the universe, this distance 1 over h is about 20 times 10 to the 9th light years. 20 billion light years. Okay. The redshift of a photon from the horizon to where we are is by this factor of 1 over 20 times 10 to the 9th. That's a lot. So the photons that we see coming from the horizon are of incredible, basically the answer is that the photons that we see have a wavelength which is about 10 billion light years. So those are not very energetic photons. We are not likely to see them. Right. What kind of experiment would we do to see them? Well, we would do the same kind of experiment we did with a black hole, except we do it from the inside. Alice takes her fishing pole, and at the end of her fishing pole, instead of a worm, she has a thermometer, and she casts it out. They got a very long line of fishing. Casts it out. The expansion of the universe pulls on the thermometer, or it tends to be accelerated out away from her, and she waits 10 billion years or so. There's also it's not just a fishing line. It happens to be a coaxial cable or something that she can read off the temperature. And she waits 10 billion light years and then puts a thumb on the spinning reel to stop it. She doesn't want it to go through the horizon. So it stops over here, and she waits until the signal comes back. That's another 10 billion years. And she reads off the temperature, and the temperature she'll read off as high. On the other hand, if she just sits here with a thermometer, the temperature that she sees is redshifted, and it's very, very, very low, far lower than anything that can be produced in the laboratory. It's not, in particular, the microwave background temperature. It has nothing to do with that. It's the de Sitter temperature. That's the properties of the world that we live in as it will be a couple of 100 billion years from now. Empty, apart from us sitting at the center, everything else having passed out through the horizon. Some amount of stuff gravitationally bound together, might include our galaxy and a couple of other galaxies that happen to be not being dragged away with the ambient expansion. And everything else will be essentially empty except for this very, very, very feeble radiation radiation from the horizon. It's a sort of grim prospect, as various people have noted. The astronomers at that time will be confused. They won't understand why they're alone in a very big universe. In fact, they'll have a very hard time measuring how big the universe is. There won't be anything out there to look at. So it will be, and the possibility of measuring this radiation, well, that's not going to happen either. Yeah. Yes, Michael.
I think what you said last week was that from our perspective, things don't exit past the horizon. So
Well,
there's a sphere against it.
Yeah. Yeah, exactly the same as the black hole. Here's the black hole. From our perspective, in a classical analysis, we would see things getting closer and closer and closer and closer and closer to the horizon. You could say exactly the same thing over here. Let's draw it. Here's our observer. Somebody falls through the horizon. Our observer over here never gets to see them fall through the horizon. As time goes on for our observer here, he looks back, and as far as he can tell, as time goes on longer and longer, Bob says Alice is getting flattened against the horizon. Yeah, so it's exactly the same as the black hole.
Basically redshift and then basically disappeared, phased away.
Fade away.
So if somebody else that's in plane falls through the exact same spot, what's bumpers so that,
Okay, classically, just without worrying about any quantum mechanics, okay, here's what he sees. Sees may be the wrong term, since the wavelengths of radiation that they send out get so long that they'll never see it. But here's the mathematical description. Let's see. All right. Here's the horizon. And here is, what was it, Alice? Here's Alice, and what's the other one? Jane. Here you are, Jane. Alice falls towards the horizon and gets squashed. Jane gets closer and is starting to get squashed. Alice gets closer. Jane also gets closer. In other words, a kind of sedimentary structure forms near the horizon that just gradually gets closer and closer and skinnier. Now, that's a classical description. What actually happens quantum mechanically is more complicated and involves interaction with the emitted radiation and so forth, which spreads them all out over the place and ionizes them, cooks them, does terrible things to them. But from a classical perspective, you would just lose track of them as they get squashed closer and closer in there, and you'd lose track of them because the radiation from them would get more and more and more redshifted as they get closer and closer. Okay.
But isn't it the case that the horizons are only hot for things that get close but don't cross over? If you pass through, you don't get cooked.
Okay. Alice has no problem at the horizon. She sails perfectly happily through. Bob just loses track of her, but if he tries to do an experiment which sees what happens to her, we come back to this very strange situation, this Heisenberg microscope situation, where the only way to do an experiment is to shine some high-frequency light on Alice, and as Alice gets closer and closer to the horizon, the wavelength of that light has to get smaller and smaller. So the answer, I'm sure by now you know, is that the attempt to look at her will cook her. So, right. Yes, Kevin.
Simplistically, all those effects of the horizon of the black hole were caused by the gravitational well, if you will, of the black hole. What's the equivalent here?
Well, there is a gravitational, all right, good. All right, let's do a little exercise. For any kind of gravitating material, which we usually call mass, but we could use the word energy, for any kind of distribution of energy or mass, there is around it or in its neighborhood or somewheres, there's a gravitational potential. All right, the gravitational potential is usually called phi. Phi is such that its derivative, its gradient, is the gravitational force on an object, on a unit mass, on a test mass, on a unit mass. Now, phi satisfies an equation. On the left-hand side of the equation is something involving phi, and on the right-hand side of the equation is the mass density. This is Newtonian physics. Let's do Newtonian physics. What's on the right-hand side? Let's just say the mass density, which I'll call rho, and it's a function of position in general. It might just be a point source at the center. What's the left-hand side? I've just written phi, but of course that's not quite right. Anybody know the right, not the divergence, but close, you're close. Something called del squared, which is basically the second derivative with respect to the distance, r. D second by dr squared of phi for a radially symmetric distribution of mass is equal to rho. This would give us, for example, for a point mass, it would give us the usual Coulomb, the usual Newtonian potential energy. Now, vacuum energy is an interesting possible candidate to put on the right-hand side, and let's do so. Is my sign right? Is del squared phi minus rho or plus rho? I can't remember, and I'm not going to try to figure it out. It's one or the other. It's not important. All right. What would happen if there were vacuum energy in addition to the pockets of ordinary energy that sit there? Well, you would put a constant on the right-hand side. What would the constant be? The constant would be the constant vacuum energy, sometimes called cosmological constant. Other times it's just called h squared. It's basically proportional to h squared. In fact, that's where h comes from. So here's a formula for the gravitational potential of a space which is filled with a uniform distribution of mass. It's the vacuum energy. Absolutely uniform. Not only doesn't it change with position, it doesn't even change with time. What's the solution of this equation? Nope. Easier than that. It's phi equals plus or minus. We'll figure out the sign later. H squared r squared. Let's differentiate. Well, maybe there's a factor of 2. What's the first derivative of this with respect to r? H squared r. What's the second derivative? H squared. That's this. Okay? So look at that. A uniform, absolutely uniform distribution of energy, and there should be a minus sign here. Yeah, there should be a minus sign here if we do it right. Okay? So what we see that there's a potential, a gravitational potential. You can think of it as being due to this uniform distribution of energy distributed all over space. And what does it look like? It looks like this. Minus h squared r squared over 2. Right? What does this mean? This means, okay, let's follow it a little bit. That's the potential energy that I, at the center of my geometry, I'm special. I'm at the center of my geometry. You may think you're special and you're at the center of your geometry, and that's fine with me, but I know that I'm special and I'm at the center of my geometry. I make measurements. I make measurements on test masses, and I find they move in various ways. And I find they move as if they were in a potential which went like this. Incidentally, what does the force do to this potential? No? The force is the derivative of the potential. All right, so the derivative of the potential is is just R. So this is a force which increases, it's repulsive, that's the minus, pushes you down, and the force increases linearly with distance. So any two objects, if you just start them out at rest, they will start to accelerate away from each other, and they'll eventually start picking up some speed. How long does it take them to pick up any appreciable speed? That depends on h. Basically 10 billion years for it to pick up any significant speed. But if you wait 10 billion years, it will be moving like a rocket. Okay. So, no, not like a rocket, like a photon, or close to a photon. All right, so what does all this mean? Supposing you start an object right up at the top, literally at the top, what happens to it? It stays there, right? It's at a point of unstable equilibrium. Well, that's another way of saying that me, in my own frame of reference, if I take an object which is located right where I am, it'll stay there. You don't have to be too sophisticated about it. If I am my own object and I don't move away from myself, well, not, sometimes, but not usually. Okay. Now, what happens if I take an object a little bit away from me? And again, we are ignoring all other forces. We can take into account the other forces we're ignoring. So I start somebody out at rest 100 meters away from me. That's over here. What happens to them? They start moving away. And in fact, in this kind of potential, they will move with an accelerated motion that will be, if we take into account relativity and everything, it'll be this exponential expansion. So that's just a statement that the space in between things is expanding exponentially. So this kind of picture is a kind of Newtonian description of the same physics as the exponential expansion of the universe. It is as though there was, number one, a uniform distribution of matter around me, and number two, a gravitational potential energy which is pushing everything away. Yeah.
But we do have to consider the other forces, right? Like,
We certainly do.
other forces,
Yeah.
even a person, the atoms would disintegrate.
Yeah.
all get pushed.
Right. So if I took let's take the potential energy between you and me. Only gravity for simplicity. All right? There's another contribution. I'm standing at the center, and I'm thinking about you, and I see that you have an ordinary gravitational Newtonian potential energy relative to me in addition to this. All right, first of all, what would the ordinary gravitational potential energy look like? It would look like that. Pulling you toward my center would look like that. One over R potential. All right, if I add that to this, it'll look something like that. So if I'm close enough, then you get pulled toward me. If I'm right at this distance, or you're right at this distance, then you're in a kind of unstable equilibrium. But if you're slightly farther away than the top of this, then you get pushed away. So this is exactly the situation that the Andromeda Galaxy appears to be in here somewhere, is falling toward us. A few galaxies away, they're accelerating out away from us. Yeah.
So this is a model just based on the expansion of space, and it acts as if it has this gravitational effect.
Yes.
But then we did talk, in describing it, we also talked about the vacuum energy, which is it's a quantum effect, has nothing to do with and it behaves the same. And so they both actually are there.
Which are both? No. There's one thing. You can call it vacuum energy. You can call it cosmological constant. There's only one thing. And if you want to mimic it or model it in Newtonian physics, you model it by a uniform mass distribution. Right. But it's one thing. It's not two. Vacuum energy, cosmological constant, dark energy, all the same thing. Okay? And they all correspond, if you, as I said, if you want to model it in a Newtonian context, you simply imagine a uniform, right.
But on the other hand, we're saying this is also a consequence of the simple expansion of space, of the relativistic.
Well, you can either say it's a consequence of it or a cause of it. I mean, they go together.
Right.
Right.
Related to this part, just a little bit of expansion.
Say it again?
Pardon the pun.
I say it again.
Pardon me.
I do.
It seems that the same phenomenon has a completely classical description and a completely quantum description.
Well, the origin of the dark energy, the cosmological constant, the vacuum energy, is most likely quantum mechanical in origin. But once it's there, it's just energy. In fact, I mean, you know, the mass of the electron has a contribution to it which is quantum mechanical. But once we know what the mass is, we simply use it in classical physics as if it were just an ordinary mass. So while it's quite true that the dark energy cosmological constant may ultimately be due to quantum fluctuations, nevertheless, by the time we average over those quantum fluctuations, what we see is a uniform distribution of energy, very small to be sure. If it wasn't small, then we'd be rocketing away from each other. It's very, very small. In natural units, in Planck units, it's something like 10 to the minus 123. It's a very, very small number compared to any other natural scale in physics. And it sets the scale for our, and it's the reason, its smallness is the reason that our horizon is so big. What would the world be like if that cosmological constant was much larger? In other words, if h was much larger. Here's the distance to the horizon, sorry, 1 over h. What if h was much, much bigger? Then we'd be surrounded by a smaller sphere. We would be living in what effectively looked like a much smaller universe, even though, what do I say, h being big, right? If h is big, that of course means a more rapid expansion, but it also means a smaller horizon. So we'd be sitting in the smaller horizon, but with a much larger repulsion between things. If h were larger, the repulsion would be larger, and the size of the horizon would be much smaller. So we'd be much more tightly restricted, but we'd also be subject to a force which would be, you know, causing everything to explode. So there is a limit to how big the Hubble constant, the cosmological constant of the dark energy can be, and we still be able to measure it, or we'd be able to talk about it. Yeah.
Would that mean that there's a relationship between Planck's constant, which is related to quantum fluctuations, and the cosmological constant?
Yes, in a sense, there's a relationship. The language to use is not Planck's constant. Planck's constant is a thing which carries dimensions. It's always good to talk about dimensionless things. If you work in Planck units, you're automatically talking about dimensionless things. And of course, knowing what the Planck unit is does involve, in ordinary measurement units, does involve knowing what h bar is. But yeah, the answer is in Planck units, and that means everything is dimensionless. It means that the Newton constant is 1. It means the Planck constant is 1. It means the speed of light is 1. In those units, where all the fundamental constants of physics, the most fundamental constants of physics are set equal to 1, in those units, the cosmological constant energy, the dark energy, is 123 orders of magnitude smaller. So that's one of the great puzzles of physics. What's the origin of that very, very small number? Yeah.
Along those lines, I have heard that not all theoreticians share the idea that vacuum energy should be identified with the cosmological constant because of that 123.
If you go out in the world and you start asking people, is the Earth flat or is it round, you'll find 40% of Americans don't know that it's, and I wouldn't say, the situation is well, let's be a little bit charitable. It's not quite as bad. Yeah. No, there are some serious physicists who question it, and but and 10 years ago you might have reasonably questioned it. 10 or 15 years ago you might have reasonably questioned it. The bounds from experiment get tighter and tighter and tighter. What they mean by saying that the cosmological constant isn't a constant is the hypothesis that basically that age varies with time and decreases, and will eventually settle down to zero. The idea that the vacuum energy, whatever it is a temporary transient thing which will settle down. All right, and eventually not be there.
Just one quick question. When they keep saying on these TV shows about how everything's getting lonely and dark and we'll be all by ourselves and all that kind of stuff, we wouldn't even notice the difference here. Because you can't see galaxies other than maybe Andromeda with the unaided eye. And
No, but with a telescope you can.
Yeah, but I'm saying without a telescope, we won't even be able to notice it.
Oh, that's probably true. Yeah, without a telescope, yeah. Yep. Yeah, who cares?
The other thing was if you said it's perfectly flat, if you took it perfectly flat and extended it forever and you tried to pull it or it'd never fall off the edge.
So? You know, it's a very interesting question. I've thought about it myself, and I've known other people who thought about it. How would astronomers of that distant time in the future, the Earth is still here, they're still here, you know, there's some questions and problems, but nevertheless, we're all still here, and we have our telescopes, and we've lost our history books. The internet has failed, we've lost our history books, and we don't know very much. How might we become aware of the fact that there was a finite horizon out there, that there was a dark energy, that things are accelerating away from each other, and it's very, very hard to imagine I can't think of any way that they'd be able to tell. The cosmic microwave background, what would happen to it?
Redshift away.
It redshifts to the point where it's completely undetectable. What about the galaxies that we count in order to measure the Hubble constant and so forth? They're not there anymore. And it just becomes very, very difficult to imagine how they could reconstruct
They would,
But with our galaxy,
New galaxies being born within the,
new galaxies are not born from empty space.
No, but they
but
would still
we're
have,
adding to it with the dark energy.
No, the dark energy won't create galaxies.
they would, actually, before we knew any of this astronomy,
Yeah.
there was something called Olber's paradox.
Right.
And so they would have to have some explanation for that.
No, there wouldn't. There wouldn't be any stars out there.
No, there would be our galaxy, and as
No, Olber's paradox, let me remind you, Olber's paradox was about the idea of an infinite uniform density of stars out to infinity. If you just take the stars from within our galaxy, how much light do they give? We know how much light they give. Olber's paradox was a paradox of what happens if the universe is filled with stars out to infinity, and they're not, he didn't know about expansion of the universe, they're just sitting there.
no, but they wouldn't know about galaxies, so they would just look out and see stars.
Yeah, but they would see an end to the stars. They would see the galaxy they would see the island universe that astronomers before Hubble believed in.
that would include Einstein.
Including Einstein.
But he stuck the cosmological term in there just in case, to make it static.
Yeah.
So they make that same mistake, so to speak.
No, they would just, they would, yeah, right.
The stars in our galaxy would be smearing against the horizon, right? So they would go out and,
No, 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 no. They'll just be just where they are now. They'll be, how big is the galaxy? 100,000 light years, right? Small, tiny microscopic size.
no, I'm saying that the horizon will be shrinking until,
Horizon doesn't shrink. Horizon doesn't shrink.
no, it's not constant yet. It'll be another 20, 30 billion years.
Okay. Right, but we're talking about 100, yes, yes, and how big will it be in 20 or 30 billion years?
Few galactic radii.
No, 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 no. It will not be a few galactic radii. It will be about 20 billion light years. From the dark energy that we know is there, from the measurements of everything we know about, the cosmological constant is a certain number. How big? Big enough to put the horizon about 20 billion light years away. Now, tomorrow, basically forever. So they'll be sitting in this big container, 20 billion light years across, with 100,000 light year galaxy that they can see, everything else having been swept clean. And how do they detect the fact that there is a outer boundary, let's call it?
But isn't there some rate at which stars are ejected from the galaxy? Because they, when they're going to
Yeah, stars are ejected from galaxy. That's true.
You'll have some small number of objects you can track for a while.
You can track them for a while, but you won't be able to track them out to well.
How do we know that that doesn't already happen?
Which? Stars evaporate from the galaxy?
That edge of the universe, that 20 billion light years away,
Is.
We're not able to see the rest of it.
We can see it. We can see it. We can measure the expansion rate and reconstruct it. Right? Where there's enough stuff around to be able to reconstruct it at the present time.
Suppose the event horizon would be just outside the distance to the Andromeda Galaxy. Wouldn't the
That would be quite noticeable.
yeah,
Sure.
then you'd be able, because the Andromeda Galaxy wouldn't behave the way it behaves now,
Right.
because the component with the
Yes, yes,
expansion is so large.
Yes. But it's not, the horizon is not going to shrink in. The horizon is going to be at the place where, it's going to be at, with the numbers that we have today, well measured, checked many different ways, the prediction for the future is that the horizon will be at about 20 billion light years. That's where it will be. Yeah. In other words, h is constant during this kind of expansion, and the distance to where you have to go to where you see the speed of light, that's going to be constant. Yeah.
Don't forget Big Bang's happening out there.
Not that I know of.
I thought the multiverse, all the, there are.
Yeah, but we can't see that part. That's out beyond the horizon. That's out beyond the horizon. That will not be visible to us or to our future descendants. Now, what is true, there is something which is true. They're called Poincare recurrences. I'll tell you what a Poincare recurrence is. First of all, your picture of, that's the inside. Your picture should be that there's some temperature here, a very low temperature from our point of view, a very high temperature out near the boundary, but you should think of it as a thermal system. It in fact has an entropy. The entropy is just the area of the horizon in Planck units. It has an entropy, a certain finite entropy. And so you can think of it to a large extent as a cavity with a finite amount of entropy in it and some thermal gas The thermal gas is mainly out near the horizon because of this effect. It all tends to congregate out here. And it's constantly fluctuating. Now, a thermal system, let's talk about thermal systems, a box of gas with lots of molecules in it. After it comes to thermal equilibrium, and in fact, what will happen is everything will come to thermal equilibrium. When everything passes out through the horizon, it will be in thermal equilibrium. What is a box of gas like when it's in thermal equilibrium? Well, it's like nothing. I mean, it's a big, dull box of uniform density. Nothing much happens. It just sits there and sits there forever and ever, right?
Black body, right?
Yeah, if it's radiation in there, it's a black body. If it's molecules in there, the molecules, and they're fairly, let's say they're fairly dense, then apart from tiny little fluctuations, nothing ever happens. Well, that depends on time scales. There are time scales. Basically, statistically, anything can happen. There are no rules. There are no rules. There's only statistics, only probabilities. That's all there are probabilities. You can really ask, what is the probability that all the molecules suddenly come together in such a way that they all wind up in the corner of the room? There's an answer to that. There's an answer to that, the probability. It is basically E to the minus the entropy of the gas. The entropy is roughly the number of molecules of the gas. So if we have a box with 10 to the 25th molecules, this is E to the minus 10 to the 25th. You wait a time of order E to the 10 to the 25th. It's called the Poincare recurrence time. And basically the Poincare recurrence time is the time scale for extremely rare and unusual fluctuations to take place. An extremely rare and unusual fluctuation might be all the molecules go off into the center. Or it might be they all assemble themselves into an elephant, or whatever. That time scale is of order what's called the Poincare recurrence time, and it's normally extremely huge. On that time scale, there's constantly things going on. Fluctuations taking place which take you far out of thermal equilibrium. So far out of thermal equilibrium that in the return to thermal equilibrium, all sorts of complicated vortices and other things might form in this before it returns to thermal equilibrium. This is also thought to be true for de Sitter space, that if you really wait long enough, how long? E to the 10 to the 120. What units? It doesn't matter what units. Believe me, it doesn't matter what units. In any units you can think of, it will take E to the 10 to the 120 of those units, and let's say years, for a recurrence to occur. And on that time scale, all kinds of things will take place. So, among other things, right? Right. But, you know, short of such impossibly long time scales, nothing will happen. It'll just be heat death. The same kind of heat death that takes place in here when everything comes to equilibrium and there's no more interesting things happening. Well, more mild fluctuations could happen. Fluctuations could happen. I'll give you an example of a fluctuation that can happen. We can even give a rough estimate of how long between such fluctuations. Instead of the whole world returning to the original Big Bang, which might happen, that would be this time scale here, we could ask for a more modest kind of fluctuation. A more modest kind of fluctuation might be a fluctuation happens in which a solar system accidentally forms. I told you an elephant could form. Okay, yes, an elephant can form. And the time scale for elephants to form is not E to the minus the entropy of the whole gas, it's E to the minus the entropy of an elephant. What's the entropy of an elephant? Roughly the number of molecules in it. In the same way, if you wait long enough, by accident, by pure thermal fluctuation, a solar system might form here. That might be the cheapest way of making an observer. Right? The cheapest way, probabilistically speaking, of making an observer might be for a fluctuation to happen and to create a solar system. But I can think of something a little cheaper. I can think of just the Earth forming. Right? That would be even cheaper. The entropy of the Earth is, well, you might worry a little bit if there was no sun, then you wouldn't have any warmth, but let's not worry about that. You might form an already warm Earth that keeps itself warm for some period of time. And you say, well, maybe it's not enough time for people to evolve. Don't worry about it. The fluctuation involves the creation of people too. Okay? But you could even do cheaper. If all you want is a single observer, you could imagine a single observer, or just his brain being nucleated by random fluctuation. Such things are called Boltzmann brains. And serious physicists worry about computing the relative probability of ordinary observers with a reasonable history like us versus Boltzmann brains. They don't want a universe in which the typical observer is a Boltzmann brain. That's not a good thing if when you calculate the properties of the universe that you find out that the overwhelming majority of observers are Boltzmann brains that appear spontaneously out of nowhere. And serious physicists worry about whether their cosmology will be dominated by Boltzmann brains instead of Darwinian brains that evolved. I'm not kidding you. This is, and it's a serious business.
About ancient aliens.
Maybe a quicker way would just be to send someone out, even though it might
Quicker way to do what?
to determine whether in the future, when you lost all your history books and the internet has crashed, to determine whether or not, if you just, because it might be billions of years, but then you might be able to see that there's...
No, you're right. I should qualify my statement that it's impossible to do it except on time scales which are big enough to explore such large regions. Right, that's exactly right. These forces are such that they only become appreciable at distance scales of, let's say, some fraction of a billion light years. So yes, if you could go out and explore, yes, of course you're right, that's a much shorter time scale. You could go out and send out your explorers, map out the geometry of, with light signals, measure the properties of space on large scale, space and time, and if you had yourself a few billion years to do it in, and rockets that could get out there and explore that large size, yes, then you could definitely tell. But if you're restricted to, the usual lifetime of an experiment, well, just any kind of ordinary time scales, you would have a much harder time telling, and I'm not sure how you would do it. Yeah, but they're absolutely right. You could imagine sending out explorers to map out geometry, and they would find this. Yeah.
So the time scale of the experiments would be redshifted.
Well, no, the time scale of the experiments would be of order a few billion light years.
You're saying that it takes longer the more you wait.
It takes longer the more you wait.
Longer to do the experiments to find out what we know now.
Yes, it would take much longer to do the experiment. Yes, that's right. That's right.
The observer sending...
No, I think you're right. It is a matter of redshift in a sense, yes.
The observer sending information back sends a radiation that is modulated.
Mm-hmm.
And that's redshift.
That's okay. We don't even do that. Don't even think about it. Just send the observers out. Let them make measurements with light rays. The light rays take 1 billion years to get from one place to another. That's okay. We have 1 billion years. And then just bring the observers back. And you're right. There is a redshift factor. But we face exactly the same redshift factor when we measure it today. We measure today the cosmological constant by monitoring the cosmic microwave background. That's been redshifted by a factor of 1,000 or so.
So what is the information content of a highly redshifted signal?
You don't have to redshift that much. If you want to explore the universe on a scale of, let's say, 4 billion light years on a side, and that's enough. That is probably 1 billion light years would be more than enough to detect the expansion. In 1 billion light years, the redshift is not a big deal. It's a small fraction of one, a tenth or something like that. So you're not limited by redshift in making these measurements. If you were, we wouldn't be able to do them today. The planets and so forth, not the planets, the stars and galaxies that we see out there that we count and which form our measuring rods and so forth, those are out pretty far, a few billion light years. But we're not limited in detecting them by their redshift from us.
Since we're talking about Poincare recurrence probabilities, and of course all this stuff is based on, quantum mechanics, quantum field theory.
No, that does. Poincare recurrences are not quantum mechanics. They're classical.
I'm not saying that's true, but all this is based on predictions on the kind of laws of nature that we are aware of today.
Yes,
What's
yes.
the probability that in the future humans will discover laws about nature that'll make all this wrong?
Probably one.
Just wanted to make a point.
But your point is well taken, but it's also true that the most single robust set of rules that has never been shaken at all are the rules of thermodynamics and statistics. So if I had to bet on which laws would be most likely to survive for a very long time, arbitrarily long time, I would guess those which were based on statistics, probability theory, namely statistical mechanics. But do we know? No.
I would also make the point that statistics and probability, what they ultimately mean, is also something that is quite mysterious, and we might have a different view of it.
Yes, I think we will have a different view of it. I was going to talk about, let's see, what time is it?
It's an hour.
It's an hour what?
It's that clock has already.
I know. What time is it really? All right. I thought I would amuse you with some other things that physicists worry about today that sound very bizarre.
I'm just going to ask if this is a good time to bring in that question that you brought up about the ultraviolet and redshift connection. I mean, infrared, ultraviolet, infrared connection.
Yeah, I never quite get to it, do I?
No.
Yeah, it is the right time, but I'm not going to do it anyway.
Maybe I come back for another 10 years?
Yeah, ooh, someday we'll get to it. I was going to tell you about a puzzle that has to do with probability theory that is really sort of obsessing a lot of physicists, and I'll tell you where it comes from. The first thing, which we're not going to talk about tonight, is the idea of, except I'm just going to mention it, it's the idea of eternal inflation. I'll draw a picture of it for what it's worth. And then I'll tell you what the nature of the puzzle is. First, we want to get a picture on the blackboard. A picture of de Sitter space or a expanding, inflating universe looked like that. Everything below here is the world. Everything above there doesn't mean anything, and this is the end of time. Okay. One of the things that was discovered, sometime in the 1970s by a physicist by the name of Sidney Coleman was that the de Sitter space like this is probably unstable. But it's unstable in a very specific way. It's unstable with respect to nucleating little bubbles in which the cosmological constant might be smaller. All right, I'm just going to draw you what the picture looks like. If a bubble nucleated over here, in which the cosmological constant was a little bit smaller, or maybe a lot smaller, what would happen is a region would grow and eventually fill up a region of space like that. This region of space in here, this region of space-time in here, is itself an entire universe. Don't ask me why. It's a bubble, but it's an expanding bubble, and that expanding bubble expands out to something infinitely big up here, and it corresponds, in some sense, to a universe. With time, many of these bubbles will form. And in fact, the population of them will exponentially increase. Why? It has to do with the exponential expansion. The population will exponentially increase. And this is a picture that cosmologists love to draw. These different bubbles could be different from each other. It's not really terribly important. They might be different from each other. Things go on in them. And this process is imagined to keep going and going and going. Now, each one of these tiny little bubbles is as big as the original one I drew here, for the same reason that this line here is as big as that line. It's just that they occur later. And they fill up all of future infinity here with a kind of fractal structure of exponentially increasing population. There could be people in there, there could be whatever you like. The populations exponentially increase. There are some very funny puzzles about probability theory having to do with exponentially increasing populations. And they have really gotten in our way. I'll give you some examples just for fun. I'll tell you some examples, and then I'll tell you how it applies to this. Imagine the following Gedanken world, a thought, it's not an experiment, it's just a world. In fact, it's not a Gedanken world, it is our world. It's a world in which the population is exponentially increasing. Unfortunately, this is approximately true. Okay. Number two, it's a world with finite resources. I think it's true.
Yeah.
But let's take it to be the case that for one reason or another, that nobody really has the vaguest idea what the total resources are. This, I think, is not true. Unless you're in Congress. One half of Congress, anyway. Right? Yeah. So we will take it. These citizens who live in this exponentially growing population, they really don't know, have no idea at all what the resources are, but they are interested in the probability that they want to know what the probabilities are that their resources will last for another generation or so. How can they give an answer to this if they don't know what the resources are? But we'll add one more postulate, and the one more postulate is one that we always make in science. I'll give you some examples of it. And it is that we who are doing the experiment are typical. Typical means the following. It means that if there are a great many possible outcomes, but by some large majority, the observers who are doing this have a large probability. Well, let's see how to say this. Yeah, okay. Let's talk about coin flippers. Let's talk about coin flippers. I hate to digress, but let's get into coin flippers. We got zillions and zillions of these people who are obsessed with coin flipping. And what they love to do is they love to flip a coin 1,000,000 times. All of these people do this. And they count how many heads they get, and they count how many tails. What they do with it, I don't know. All right. But a typical one of them asks the question, what bet should I make for how many heads and tails do I get? Not exactly, but within some reasonable bounds. I'm going to do an experiment. I'm an experimental physicist. All experiments involve statistics, especially in quantum mechanics. And when we make predictions, we're making predictions analogous to the prediction of coin flippers who flip coins. Well, what's the answer? The answer is there are some coin flippers who flip all heads. There are some coin flippers who flip all tails. According to the standard theory of probability, the overwhelming majority flip about, what did I say, a million flips? A million plus or minus 1,000, square root of n, right? So if you're at all smart, and you're a good experimental physicist, and you know the rules of statistics, you will put down your prediction. Your prediction will be, what did I say, 500,000 plus or minus 1,000. I think I probably said it wrong. 500,000 plus or minus 1,000. That'll be your best guess. And if you're very far away from it, you'll probably say there was something. You probably won't believe that you are an outlier. You're more likely to believe that your theory was just wrong. But there are going to be those people who are outliers, and they, of course, will believe their theory is wrong, and they'll be wrong. We always make the assumption that we are typical. So in this expanding population, let's make the assumption that we are typical. We are like the majority of all observers who ever lived. Then what bet do we make for how long the resources will last after the present time now? Well, not necessarily the last one, but there won't be more than 2 or 3 generations after us. And the reason is, in an exponentially expanding population like now, about half the people who ever existed exist now. About 3/4 of the people who ever existed within 2 generations. About 7/8 within 3 generations. So if we're typical in an exponentially expanding population, we are near the end of that expansion. We're near the end of that expansion. Now, that's a very puzzling conclusion. It sounds like there's something wrong with it. How can you possibly know that if you don't know what the resources are? On the other hand, it is true that no matter what the resources are, most people will be near the end of the resources. Right? This is, I'll give you another example of this kind of exponential expansion. You've all seen, I'm sure you've seen, it's my favorite drawing. I come back to it over and over again because it has some deep mathematical significance. It's Escher's drawing called limit circle number 4. You've all seen it, angels and devils, and I'm not going to try to draw angels and devils, but it has a big angel. Let's just restrict ourselves to devils. I prefer devils. It has a big devil in the center. It has smaller devils out here. It has smaller devils out here. And so forth. Now, in fact, the geometry is such that they're really all identical to each other. There are symmetries of this diagram which move points, which can move this point into this point. It'll move this point into something small over here. It's just the way that it's drawn makes some things look smaller and some things look bigger. It's completely symmetric. But of course, when Escher actually drew it, he did have to draw the small things small and the big things big. Now, here's the question. Let's define an angel, or devil, excuse me, a devil which has been drawn with a body part missing. Let's call him an amputee, okay? Definition of an amputee. If the devil was drawn with some body part missing, we'll call him an amputee. Now these devils go to sleep and they wake up in the morning and they wonder, am I one of the unfortunate amputees, or am I one of the whole devils? Okay. If you look at Escher's drawing and you extrapolate Escher's drawing past the last visible devil, and you believe that you can extrapolate it, you'll see Escher was awfully good at drawing. He didn't draw any devils with missing body parts. So your conclusion would be, a very high probability you're not an amputee. Okay? On the other hand, Escher had finite resources. Finite patience, finite time, finite amount of ink. Right? And that means as he got tired out near the very, very edges, surely very, very close to the edges, you'll find that almost all of the angels and devils will be slightly misdrawn. Right? Of course they will be. They won't have heads, or they won't have tails, or whatever it is, the ones out near the boundary. Now, what is the ratio of the ones which are adjacent to the boundary to all of them? Do you know the answer? No. No. There are about as many out near the boundary as there are in the whole thing. Not, obviously, there are fewer in the boundary, a factor of a half. And that's because the number of them grows exponentially as you make bigger and bigger circles here. They grow exponentially. And so if you actually count, if you cut it off, let's say, by putting a circle around here, now count all the ones that are adjacent to the circle and all the ones on the inside, you'll find they're about equal. It's the same mathematics as saying about half the population, no matter how long into the past the population had been growing for, today about half the population, one generation constitutes about half the population of anything that ever existed. In the same way, about half of the devils are right on the edge, wherever the edge is. We don't have to know how much resources Escher had. It doesn't matter how much he had. No matter how much he had, as he draws more and more and more of them, the ones near the edge will always be about half of all of them. And so, if you wake up in the morning and you don't know whether you're a whole devil or half a devil, the chances are about 50% that you're half a devil, that you're an amputee. This is very puzzling because you could say, well, how can I say that when I don't know how much resources there were? Well, the answer is it doesn't matter how much resources there were. Okay, now we come back to here. Okay. We are again facing a problem of exponential population growth. In this case, population of little bubble universes. Let me come back to angels and devils for a minute. Come back to angels and devils for a minute before we go on to universes. Escher did have angels and devils. Let's ask a different question. The different question being, when you wake up in the morning, are you an angel or a devil? 50% probability, right? There are as many angels as devils. And the mathematics of Escher's drawing, if it went on for infinity, in some sense that would be true. But we know that Escher had finite resources, which means we have to draw an edge to this. The answer for the ratio of devils to angels is extremely sensitive to the way we draw that line. It's extremely sensitive to the way we could draw the line. For example, every time we come to an angel, let's go around it that way. Every time we come to a devil, we go around it that way. And now we push this edge out further and further. By a factor of about 3/4, we will have more devils than angels. It's all in the edge here. It's all in the edge. And so the assignment of probabilities to angelness or devilness is just extremely sensitive to what Escher did just as he was running out of resources. It's ridiculous because you simply don't know anything about his resources. You would think that the answer was 50-50. But if at the end he had a little bit less pink paint than white paint, the answer would be many, many more white than pink. Okay. Same exact thing here. You want to know the relative probability of different kinds of bubble universes forming, blue ones, pink ones, and so forth. The population is exponentially growing. How do you decide? You try to decide the same way. You say, let's chop this off at some time and count the number of blue ones versus pink ones. But the problem is the answer is super hypersensitive to the exact way that you draw this line. And that has led to a problem that cosmologists, physicists like myself call the measure problem. Measure as in probability measure. How do you assign probabilities in a world of exponentially increasing populations? And the answer always is it is extremely sensitive to the way that you cut things off, to the way you, and your imagination in the universe. This is a very, very big problem for cosmologists because they want to be able to use their theories in a predictive way and make predictive predictions. What other kind of prediction is there? Or at best, or if not predictions, at least explanations of things. And so in this kind of world, if it's really true that there's an exponentially increasing population, we run into new kinds of questions about probability theory and about how the use of statistics, which really just have really baffled us. My guess is, of course, that we're asking the wrong questions. We're probably asking the wrong questions. But that doesn't help to say that we're probably asking the wrong questions. It doesn't help unless you can say what the right questions are. And yeah.
Is there any connection to the renormalization or to the odd and even strings?
To which?
Odd and even, I remember it as odd and even strings, but those would be fermionic strings, where the number of, whatever you call it, the number of quantum mechanical oscillators varies the spin of the string.
Well, there are relations with renormalization theory. There are relations with renormalization theory. Renormalization theory is also a situation where, again, you start your picture of the world as having a finite number of degrees of freedom per unit volume. And then you double the number of degrees of freedom in each volume. And then you double it again, and you double it again. You don't double it really. You double it in your imagination and ask how things converge. What we're talking about, of course, is you start picturing the world as a lattice. You can't handle a continuous infinity of degrees of freedom. So you start the world as a lattice, and you make your calculations based on 1 degree of freedom per unit Compton wavelength of an electron or something in quantum electrodynamics. Then you say, I want more accuracy, so I divide the world in every cell in half again. And I recalculate. And in each case, I ask the same kind of questions. What's some relative population of regions of space with this property or that property? And again, not with respect to real honest time, but with respect to your mathematical sequence of descriptions. The population is exponentially increasing. Again, you get infinite answers. You have to deal with those infinities. And in quantum field theory, there are techniques for asking questions which are not sensitive to the, let's call them the edge effects. There are techniques for extracting out things which are not sensitive to the details of how you chop this up. So yeah, there are correspondences and similarities between questions in quantum field theory and these kind of questions in cosmology. And people are trying to exploit those similarities, but not, I must say, with any great success yet.
That bubble, is that like similar to inflation going to the current universe or something like that?
Yeah. Yeah. Well, what's called eternal inflation, creating, yeah, it's deeply connected with inflationary theory. Yeah.
Can two nucleations be close enough that they interact?
Mm-hmm. And if they did, we should see it on the sky. There's a little funny patch on the sky. There are funny patches on the sky, and there are, again, very serious physicists, astrophysicists, cosmologists, trying to sort out the details of what you would see on the sky if two of these bubbles collided. We more or less know. You'd see a small patch on the sky which had either a little colder or warmer temperature. And of course, you do see patches on the sky with a little bit of warmer and colder temperature. But to be more detailed, you'll have to get really detailed to see that that's what they are. One of the details would be the polarization of the microwave background around them. It's kind of interesting. If you saw one of these patches in the sky, and there is one, it's called a cold spot. A cold spot, and nobody knows what it's due to. It's a cold spot on the sky. A cold spot in the sense of microwave background. All right, cold spot's a candidate for a spot where another bubble collided with our bubble. It's a candidate. What more can you say about it other than it's a candidate? Well, you can try to work out in more detail what such a patch would look like. And so, for example, you discover that, that light is polarized in particular. This is the direction of polarization around this in a particular characteristic way. And people are doing this. They're working out the consequences of such a bubble collision. Of course, should this be confirmed, that it does look like a bubble collision, and in detail it does, this, of course, would be a major, major revolution in cosmology. The discovery and detection of other bubbles which collided with our bubble would be very, very major. So, yeah.
The difference is the inflation factor, the H in these regions that distinguishes the bottom from
Yeah.
the tops. Is the bottom region expanding faster? Or
Bottom region typically is expanding faster. And our region is somewhere in here, and it had a history of different expansion rates. Yeah. Yeah. So it's complicated. It's a complicated story. But it does include this idea of exponential population growth. So one could foresee a situation in which we truly confirmed that there were bubble collisions with our world. We would have confirmed something like this picture, at least a piece of it. Then it becomes a really serious matter to try to get predictive and to ask what the relative probabilities of different kinds of bubbles are. And that's where we run into this trouble of exponential population. The answers would be very dependent on the question of whether there were finite resources or not. What is a finite resources? I don't know what finite resources, just this it comes to an end somehow. And the details of the way that it came to an end would be, determine what relative probabilities were.
Bubbles colliding, you just add the dark energies of the two types?
No, it's more complicated than that. The place where they collide, depending on details, there's something called a domain wall, which separates them. And the domain wall on one side has one behavior, the domain wall on the other side has another behavior. But the point is the domain wall would be visible to us, or could be visible to us. We would need a bit of luck. Here we are. Here's our observer. If the bubble collides over here, some sort of bubble collision over here, this observer doesn't get to see it. But if it collides over here, then he does get to see it. So there's different scenarios, different situations. But it doesn't seem totally out of the question with the numbers that we know that there could be bubble collisions, that there could be visible bubble collisions. And if so, they have a particular signature, a particular behavior. They're fairly characteristic. And if the cold spot is such a bubble collision, we will know. We will know in time. What do I bet? Well, I don't know what to bet, honestly.
Do the bubbles have 4 dimensions?
Yeah. Well, they could, yes.
What about the curvature of expansion? What about the curvature of expansion, like whether it's convex or concave or flat? Would that mean that you see different things?
These bubbles are usually negatively curved Friedmann-Robertson-Walker universes. They have negative spatial curvature. The bubble collision would certainly modify the curvature in some characteristic way, but it wouldn't turn the world from a world with a negative curvature to a positive curvature. That it couldn't do, but yeah.
Kind of a related question, but is it possible to assign a probability to the statement that string theory is correct or incorrect, given that we have almost no empirical evidence one way or another?
I don't think so. I don't think so.
50/50 would probably.
That's a matter of individual opinion, for which I don't think there's any value in trying to assign a probability.
No, but I mean, is there any,
And I'm not even sure I know what it means. All right, I'll give you an answer that I've given before. There is a mathematical structure, a very precise mathematical structure, which exists. It's mathematically consistent. Mathematicians have won big prizes for proving theorems that were first suggested by theorists on the basis of string theory, which the mathematicians didn't know. So the consistency of the internal consistency of it has been extremely well checked. There is a structure. The structure has gravity and it has quantum mechanics in it. Right? So in that sense, string theory is a well-defined, exact. Now, of course, there's a very remote possibility that somebody will discover an inconsistency in it, but it seems extremely unlikely, a mathematical inconsistency. On the other hand, that part of it, which is mathematically precise, let's call it string theory with a capital S, with a capital letters, string theory, capitalized. It is supersymmetric. It is, it's supersymmetric. The world is not supersymmetric. The world, as we see it, is not supersymmetric. The mathematical structure, which is well-defined and for which we have a lot of confidence that it really exists, you can call it quantum gravity with supersymmetry, it is not the real world. So in that sense, we know now, no question, string theory is not the right theory. Okay? 100%, we know it for sure. The breaking the symmetry, nobody really knows how to do. Okay? It is not part of the mathematically precise part of the theory. We all expect that this thing that we call capital string theory, there it is, string theory, it has many, many, many different versions. A huge number of different possibilities lie within this. We all expect that it's contained within something bigger that we don't know how to analyze. It's more or less like the situation where, maybe it's like the situation where physicists in the time preceding Newton might have discovered the formula F equals ma, and the formula, the force is equal to m1 m2 times g over r squared. But they didn't have the mathematical tools to analyze anything but the simplest orbits. So they said, all right, we will use symmetry, the symmetry of circular orbits. We need one little bit of extra information. We need to know the acceleration of a circular orbit. That's not too hard. You can do it on the basis of some simple symmetries. And you can therefore figure out Kepler's, which one of the laws is it? One of the Kepler laws which tells you the period is a function of radius. Right. You know that the theory that you're working with, the theory of circular orbits, is not correct. But you just don't have the mathematical power to be able to go beyond it. I don't know if that's what the real situation is, but it could be like that. So we know that the theory of circular orbits is contained in something bigger, don't know how to analyze it. We know that the perfectly idealized supersymmetric string theory, the one that we really know how to analyze, is not the real world. It looks a little bit like the real world, but it's not the real world. And the question is whether it's contained in something bigger, which we could call string theory with a small s. But the answer is we don't know very much about this. We know a great deal about this. This has been enough to tell us all sorts of things about the combination of gravity and quantum mechanics, things about black holes, things about all kinds of things. But to say one way or another, what's the probability that string theory contains or that there is an extension of it, a bigger version of it that contains our world right over here? I don't know. Of course, in some sense, well, of course that's true. Our world is someplace. Here's the theory of someplace. If you add this to this, you get something bigger. But that's not helpful. We want to know whether in some interesting way the theory of the real world is some extrapolation from what we already know. And that there's no way to know.
Does it contradict, the string theory contradict this possibility?
Only capital string. Does it contradict the possibility that what?
Does the capital string theory rule out
The capital string theory doesn't rule out the presence of, that doesn't rule out the existence of small string theory. But what it does say is that nature is not, as we know it, is not described by capital string theory. All right. So we know with certainty that a bigger structure has to be found, and whether that bigger structure that contains our world will sort of be contiguous with, connected to, the smaller structure of capital string theory, this we don't know. We can all make our bets.
Saying that string theory has no symmetries breaking like the Higgs particles and things like that? Or?
No, people write loads and loads of papers about the symmetry breakings of string theory. The symmetry breakings in particular are the symmetry breakings of supersymmetry. And we know a lot about the mathematics of supersymmetry, but we don't know a precise version of how to combine the breaking of supersymmetry with string theory. That is outside the scope of what we know. That doesn't stop people from, you make an approximation here and there, and then you start rolling, and you can do some things. The problem is that you're making approximations, but you don't know what those approximations are approximations to. You make some standard approximations that we use all the time, and you start calculating, but there's no backbone to the thing that you're approximating. So at the present time, I think the safest thing to say is string theory as we know it and as we can, the rigorous version of it, is certainly not the real world. There's, in my view, lots of reason to think that the part of it that we know about is not the whole thing, that it could be bigger, it probably is almost certainly bigger. But how to say whether the real world is part of it, that's very much a prejudice that different physicists share in different proportions.
Does string theory, it contains gravity, does it contain special relativity, or is special relativity a postulate for string theory?
No, it really does require special relativity. Now, special relativity can be violated by the environment. We're sitting here in a room where everybody's at rest, right? And the world does not look Lorentz invariant to me. Your presence here violates my sense of Lorentz invariance. It also violates, we talked about this last time, didn't we? Yeah. So you can have what physicists call a background, which means stuff in it, which picks out a particular frame of reference. But the underlying rules for string theory do have Lorentz invariance.
It's a prediction. It's not a postulate.
Yeah, I would say it's a prediction, but the most robust, yeah, I think so, but the most robust prediction is that it has gravity. There's just no way for it to not have gravity.
It has gravity, but is it consistent with Einstein's theory of general relativity?
Yeah.
It is. Yeah. I mean, the background independence, the general covariance is in the string theory also.
Yeah, this question about background independence is a confusing one that that yeah, it is background independent up to a point. Up to a point, yes. It's hard to change the asymptotic boundary conditions continuously, but it should be hard to change the asymptotic boundary conditions continuously. How do you change asymptotic boundary conditions continuously? You can't do any operation that would change them. But short of asymptotic boundary conditions, changing the background locally in space-time, yeah, string theory does have that. You don't have to take my word for it. This is something that's been long studied since the 1980s. Works of people like Curtis Callan and other people have studied that. No, we're finished tonight. Yeah. Okay, so.
For more, please visit us at stanford.edu.